And the first way we will look at is what is called as the method of bagging, which is one technique to deal with this bias variance trade-off in a nice way. And the second method that we will do later is what is called as boosting. So, what is bagging? So, bagging stands for bootstrap aggregation, and we will talk about what these two terms are in a bit. Bootstrap aggregation. So, this is based on the idea that let us go back to our standard maximum likelihood estimation, right. So, just to draw an analogy. So, if you had x1, x2 xn as n different samples all drawn from some Gaussian with some unknown mean and let us say variance 1, or variance can be anything, let us say it is a known variance. So, I have to come up with an estimator for the unknown mean. So, let us say mu hat 1 was just x1 or mu hat 2, the second estimator is x2 and mu hat n is xn. So, what I am doing is I have a bunch of data points, all real numbers, all are drawn according to a Gaussian distribution with some unknown mean and variance. Imagine a simple example, maybe the unknown mean is 5.5 and if I draw points from this I might get 5, 7.3, 6.7, I do not know, 8.2 and so on and so forth, right. So, I get a bunch of data points. Now, I want to estimate this 5.5. I only have this data with me and I want to know what is the mean of the Gaussian that generated this data. Now, one can come up with different estimators, right. So, now it is an estimation problem, we are free to choose whatever estimator that we want. Let us say I estimate my mu hat 1 as just the first value 5, or I will estimate mu hat 2 as just the second value which is 7.3 and so on. Mu hat n is, let us say the last value is 9, mu hat n is 9, right. So, that is what I am saying as mu hat 1 is x1, mu hat 2 is x2 and mu hat n is xn. Now, we all know that these are not the best way to estimate the mean of a Gaussian. What might be a best way to estimate mean of a Gaussian? Good time to pause and think. It is just a recollection thing that we have seen this already. A good way would be to do something like a maximum likelihood estimator, which would give me 1 by n sum over xi. It would just be the sample average, right. Now, one can argue that why do we do this sampling, right? Why do we do this averaging, right. So, what is the benefit that we are getting from this averaging? So, now if you were to measure how good our estimator is in predicting the truth, then we can there are two ways to measure this, right. So, one way to say that you have an estimator and then you look at the expected value of this estimator, let us call this estimator theta hat. You are trying to estimate parameter theta and then your estimator is theta hat, and then you look at the expected value of this theta hat because your estimator is a random quantity, because your data is random, your estimator is a function of the random data, it is also a random quantity, and you can ask what is the expected value of theta hat. Well, if it is an unbiased estimator, which means that your estimators on an average is going to behave like your truth, right. So, which means that it is actually measuring the truth in a good way. So, your expected value of theta hat should be theta. In this particular case, our theta is 5.5, which we do not know, we just have one sample and then we can treat this as some random variables x1 to xn that we have, and then our estimator is some function of this random variables. So, what would this function be? This is a function which would, given n random quantities, would just pick the first random quantity. The mu hat 2 would be given n random variables, it will just pick the second random variable and output that as the answer and so on. Whereas mu hat ml would be given n random variables, it would average the random variables and output. Now, if you look at this notion of this is unbiasedness, unbiased estimators. Now, if you think about which of these are all unbiased estimators, in other words, if I ask the question what is the expected value of mu hat 1, what is the expected value of mu hat 2 and so on till mu hat n, and what is the expected value of mu hat ml, then we will realize that all of these are unbiased estimators, right. So, the expected value of mu hat 1 What is this? Because mu hat 1 is just x1, but what is x1? x1 is a Gaussian with mean mu, is a sample from a Gaussian with mean mu and some variance 1. So, what would be its expected value of a Gaussian with mean mu? Well, it is mu, right. So, this is 5.5 in this case. So, the same thing holds for all the n data points. So, in expectation all of these are the same, it is correctly identifying the truth, which means these are all unbiased estimators. On the other hand, we still think that it is a, so is I mean expected value of mu hat ml is also, we can show it is mu, right. So, because expectation is a linear operator, it will just be the average of the expected value of xi's, and each expected value of any xi is mu, and so it is an average of mu's, which is mu. Now, then we can just say that only looking at biasness is not a good idea to say whether estimator is good or not, because in that case all these estimators are equally good, but we know that x1 is going to fluctuate a lot, because if I draw another set of samples x1 to xn, x1 dash to xn dash, now my estimator is again mu hat 1 is just going to look at the first value and then predict that as the true mean, but then there is going to be a lot of fluctuation. But then when you do this averaging, the fluctuation reduces significantly. The way we formalize fluctuation is by using the notion of variance, right. So, the reason why you do averaging here is to reduce variance. So, the main idea here is averaging reduces variance. When these what are you averaging over, right. So, x1 to xn, these are all IID samples, independently drawn samples, they are not correlated at all. When you have decorrelated set of random variables, then when you do averaging, it typically reduces variance. So, what we are going to do is we are going to take inspiration from this idea and then see how it can be applied to classification problems. For that, we are going to do the following, right. So, we are going to do bagging, which is going to work as follows. Let us say we had access to data sets D1, D2 till some dm, where each di has each di, let me say each di has n data points. Let us say somebody gave us m different data sets, where each data set contains n points. What are these points? Well, these are just feature comma label pairs. It is a classification problem. For example, your D1 could have x1, x2 dot xn. Let me put a 1 above to indicate it is D1, where each x1i is independently drawn according to some underlying distribution p. And of course, it is not just xn. So, you also have y associated y with this, which is where x1i is in Rd, let us say, and y1i is in plus or minus 1. Basically, you have a classification data set, a standard features comma label pairs, and you have n of them. Each data set contains n of them. Now, each of this is independent of each other, right. So, that means that somebody drew n different data points from the underlying distribution and gave me D1, again drew n different data points, gave D2, and so on till dm. Now, what you could do is, you can run, let us say, your weak learner, which is, let us say, in this case, let us say we are running a decision tree to complete depth, which means we will overfit this, let us say, and then we get H1. Now, you can again run another decision tree on D2 to get H2 dm to get HM. What is each HI? Well, each HI is a mapping from Rd to plus or minus 1. It is a classifier, right. So, it is a decision tree. So, which means that if I give a plugin and if I give a new test point x test, HI of x test is going to tell me what is the prediction of the ith decision tree on the test data point. So, now what is happening is that you can imagine as if each of these classifiers are independently trained on different data sets, right. So, now they might, because they are trained till in this case we are making it to overfit, they might have high variance, they might suffer from high variance. If you change the data set a little bit, these predictions are going to go off a lot. Now, one way to reduce this variance is by doing an averaging. That's what our statistical methods that we have seen so far, at least in the simpler sense, simpler cases where we are drawing from random variables and so on, suggests us. Why not use the same thing here, right? So, what you can then do now is that you can, aggregate all these classifiers into a classifier H star, where H star of x is just, what you are going to do is you are going to look at Hi of x. Each of these is a plus or minus 1 value. So, this whole thing is going to be between minus 1 and plus 1, and then you can look at the sign of this, right. So, where sign, in this case I am defining sign of x is plus 1 if sign of, let us say, z is plus 1, z is greater than or equal to 0 and minus 1 otherwise. So, basically what you are doing is taking majority vote, right. So, when will the sign be plus 1? If majority of H1 to Hm say the actual label is plus 1, then the average would be positive, otherwise the average is going to be negative, right. So, basically what we are doing then is, if we had access to m independent training sets, then what you could do is you can average the decision trees or the learners that you get from each of these independent data sets to come up with an aggregate classifier. So, now this aggregate classifier will have lesser variance than the original classifier. The original classifier had less bias, because we started with classifiers which did not have too much bias, because these were overfit classifiers. So, now when you average them, you ideally want a classifier with less bias and less variance, because that's what your error, that's when your error will be low. But you only have less bias high variance classifiers. Now, the idea is to average them to get less bias low variance classifiers. Hopefully, you would have a better classifier in that sense. The only problem with this approach is that nobody is going to give us m different data sets, right. So, we are only given one single data set and not m different data sets. So, if we had access to m different data sets, then yes, we can run separate classifiers on each of these and then we will be happy. But the problem is we do not, right. So, now we have to somehow create m different data sets from a single data set that we have. So, what we have in hand, our input is just a single data set D, right. So, D, which has x1, y1 dot xn, yn, where xi's are in Rd, yi is plus or minus 1. Now, how can we create m different data sets from this is the question. Now, there are different ways to do this. The most straightforward immediate way that one can think of is, well, I can just take my n different data points, cut it into m pieces, right. So, each of these pieces independent of each other and things are fine. But the problem there is that you cannot create too many pieces, because the more the pieces that you create, the smaller these data sets are going to become. And so, your trained classifier is going to work on a very small set of data points, and that is a bad idea, because if you have too many pieces, then you do not have enough information in each of these data sets that the decision trees or the weak learners that you are training can take advantage of. So, you have to come up with an alternate way where you cannot divide this into different pieces, yet you want many data sets. That seems to be contradictory, right. So, how can we even do that? Well, the only way you can do that is if you allow some data points to be repeated across these different data sets. And that way of creating data sets with repeated data points, potentially repeated data points in each of these data sets, is that procedure is called as bootstrapping. So, what is bootstrapping? Well, bootstrapping is basically sampling with replacement. What does that mean? That means that maybe you have a data set, x1, x2, x3, x4, x5. Now, what I am going to do is I am going to create a bag. It is called a bag, and that comes from the term bagging. So, which is just a data set D1. So, this is D, Now, this bag is also going to contain 5 data points, because the original data set contained 5 data points. And the way I am going to create this bag is I will first sample without replacement from x1 to x5. That is, I put my hand inside the data set D, close my eyes and then pick a data point, right. So, let us say that data point was x3. Now, sampling with replacement, I should not have said without replacement, with replacement. So, next what I do is I put back this x3 into my original data set and then again mix it uniformly and then put my hand and pick one data point. I might get a x4 this time. Next time I might get x5, right. So, if I do this again, maybe I will get x3 again. The next time I might get x5 again. Now, this is a bag that I have created from my original data set, where I have sampled, with replacement each data point uniformly at random. Now, I can create another bag like this, which is a bag D2, right. So, this might be a second bag, bag 2, this is bag 1. This might have x1, maybe if I pull it again, maybe I will get x1 again, next time I might get x5, next time x4, maybe I will get x1 again, right. So, anything can happen because these are uniform draws. So, what you would do in bagging is you start with D and then create these uniform sampled with replacement bags D1, D2 till Dm. And now, once you have these bags, each with n data points, original had n points, this also has n points and so on, this has n points. Now, you do whatever you want to do, right. So, you run this over a weak learner, it could be a decision tree, it could be something else also. This is a weak learner and then you again aggregate these things. Well, you get h1 here, h2 here, hm here, and now your h star of x is just 1 over m, well, sine of 1 over m sum over I h I of x. So, this procedure which does 2 steps. One is the first step, which is this part, which is the bootstrap part, where you are bootstrapping from your single data set to create m different data sets, and then this is the aggregation part, where you are aggregating m different classifiers into a single classifier. These 2 steps are involved in this way of doing ensembling, and so this is called as a bootstrap aggregate classifier, or in other words called a bagging classifier. Bagging stands for bootstrap aggregation. Now, one of the common ways, of course, the D1 to DM. So, one can now ask the question, well, there are points that are going to get repeated in each of D1 to DM. So, what can we say about the amount of repetition that happens in each of these bags, right? So, if you think about that, how am I creating D1? Well, I am creating the first point in D1 by, picking one point from D uniformly at random. Now, what is the chance that that point does not appear in DM? Well, that chance is 1 minus 1 over n, because with 1 over n chance that point would have appeared in D1. Why? Because it's uniformly at random. If there are 5 points, there is 1/5 chance that each point appears in my bag when I pull one data point the first time. But now if I am asking for the probability that a point does not appear in the bag, well, that's going to be 1 minus 1 over n. Now, this happens. So, if a point does not appear in the bag at all, this does not miss the first time I am picking it, it misses it every time. And then I am picking n such points, and every time I miss a particular point, well, what is the probability that happens? Well, that probability is 1 minus 1 by n into 1 minus 1 by n so many times, n different times, because these are independent trials, n different times I am missing it every single time. So, this is the chance that a point does not appear in this bag. So, what is the chance that it actually appears in the bag? Well, it actually appears in the bag would be 1 minus 1 by 1, the chance that it does not appear, right. So, this is the probability that some x belongs to a bag D, Di, right. So, xj belongs to Dj is this, right. So, now this probability is something like 67%, right. So, because for large n of n, right. So, for large n, this guy looks like something like 1 minus 1 by e, where E is 2.7 something, right. So, the 1 minus 1 by E now looks like 67%. So, what does that mean? That means that 67% of the points kind of on an average appear in each data set, which means that there are going to be some 30 to 33% of repetition on an average in each of these data points. Now, if I learn a weak learner which is kind of overfitting, what does that overfitting means? Well, the overfitting would fit the noise that is specific to this 37% or this this data set which has a lot of repetition. But then the points that get repeated in each of these data sets is completely different, right. So, which means that you are fitting different noises in each of these weak learners which are overfit models, let us say overfit decision trees, and then when you actually average them, what happens is that the noise hopefully gets averaged out. And so, you do not lose out so much on the bias, but then your variance actually reduces, right. So, you are still having a complicated classifier, mind you, right. So, because it is a combination of multiple classifiers, but then the hope is that the noise gets averaged out, and we can see this in practice actually. So, if you plot the bias and variance of the classifier, as you add more and more trees or weak learners, what you will see is that the variance actually comes down, but the bias stays afloat. So, which means that the main reason why somebody would want to do a bagging is to reduce variance, right. So, the main message here is that bagging reduces variance. Of course, if these weak learners are completely on, these weak learners are totally not correlated with each other, then the reduction in variance will be large. So, now what people do is a lot of specific ways of making sure that these learners that you are learning are as less correlated from each other as possible. So, one way to do that is what is called as a very popular technique. It's called as a random forest technique. Random forest, which is one of the very commonly used classification algorithm ensembling technique in practice. What it does is, well, the first thing is it bags decision trees, typically overfit trees. What you do is you create these data sets and then D1 to DM and then fit a overfit tree for each of these. That is, you don't cross validate or anything, you kind of grow the tree so that it becomes as pure as possible. That is, you get to zero training error. Then what you do is, in addition to this, when you are actually fitting this tree, you do some interesting things, right. So, you do something called as feature bagging. In addition to overfitting this tree, you do something called as feature bagging. What is feature bagging? Well, the reason, you want to overfit trees which are high bias, but then which are low bias, but then you want the trees across these bags to be as decorrelated as possible. One way to achieve that is using feature bagging. In feature bagging, what you do is when you are running this decision tree, right. So, when you are building this decision tree, remember how we built the decision tree. Well, at every node, to decide on which is the next node, what you do is you look at all the features and all the splits and then see which feature threshold, feature less than threshold question gives me the highest reduction in impurity, and then using information gain or Gini index or different measures of impurity, whichever your favorite measure of impurity is, you look at which feature threshold value gives you the most decrease in impurity, and then you pick that. Now, this means that if I am building these multiple trees, all the trees are going to use all features. Now, feature bagging would tell us that pick a subset of features to consider splitting on for every node of your tree. What does that mean? That means that you have feature 1, feature 2 till let us say feature D. These are your D features, let us say height, weight, whatever, right. So, you have let us say 1000 features now. what you do is you want to ask the question, well, fi less than theta, which is the best fi less than theta for my data set. I have already created the data set. Now I need to build the tree. Now what I am doing is I am kind of doing feature bagging, which is to say that to decide fi less than theta, what I would do is I will not use all the features, I will only subsample a set of features. So maybe if I subsample a set of features, maybe I will get f1, f5, f23, f40. Maybe I get 4 features, and now only among these 4 features I ask the question which is the best feature to split on. Now maybe that will give me something, maybe F5 was the best feature in this case. Now here to decide which is the best feature, now again I subsample a bunch of features, right. So in this case maybe I will get F1, F10, F40, F20. Maybe something like that, right. So, and then I ask among these features, I pretend that this is my data set has only this set of features, and then I ask the question, well, how can I find the best feature comma split here, right. So, if I do this at every split, decide which is the feature that I need to pick in a random manner, then different set of features are being used by different trees, and then hopefully they will get decorrelated a little bit more, and so when you are averaging them, the variance reduction will be larger, and that is what is observed in practice as well. So random forest is basically feature bagged decision trees, right. So you do bagging, but then you also do this feature bagging. If you do that, then they are called as feature bagging, and this is a very, very popular technique that is commonly used in practice today. Again, so there are several variants of random forests. So you can do this for classification, you can do this for regression, where you replace your decision tree with a regression tree, and so on and so forth. We won't discuss everything in detail, but it's good to know that random forests are very powerful techniques for variance reduction, where your bias does not typically increase, but then your variance goes down, and so the error of the resulting classifier typically goes down. Good. So again, so there are several more variants as I mentioned. One variant would be to even look at the set of splits, the threshold values that you want to use in every split, right. So you can kind of also randomly sample that and so on, right. So you can do a lot of ways to decorrelate these trees, but then the usual standard practice is to just use decision trees as your weak learners, overfit them and then but then at the same time do feature bagging as well. So one typical point that in practice what happens is that the number of features that you would use when you do this bagging is approximately square root of d, right. So if you start with d features, at every round what you do is you only pick square root of d features to build your tree on, to decide which is the best feature comma threshold value. And there are some theoretical reasoning as to why square root of d is a good idea in classification problems. In regression problems, I think the suggested value is something like d over 3 or d over 5, something like that, but order of d, right. So again, so these are rules of thumb. Typically in practice, you can try out different values also and then pick one that works best, right. So depending on how much computational time that is available. So one of the biggest advantage of this approach of bagging is that these weak learners, right, so can be run in parallel, because we don't really need these weak learners until we come to the aggregate stage, right. So basically now, because if you have a powerful CPU, right, so with a lot of cores and so on, right, so you can kind of run these weak learners in parallel and then get these decision trees in parallel. And then the aggregation, of course, during aggregation you need all the trees, but then before that step you don't need all these. You don't need to wait for one weak learner to complete to start with the next decision tree, right. So and that's why this is also preferred a lot in practice, because you can run these algorithms very fast in parallel, right. So that's one point I also wanted to mention. So there are 2 points which we want to consider here before we move on to our next algorithm. One point is, right, so there are 2 steps. Basically, there are 2 steps in bagging. First step is bootstrapping, which is sampling with replacement, well, uniform sampling with replacement, and the second is aggregation, which is average. Now, both of these are choices that we make to kind of ensemble the classifiers. We decide to create these bags by uniformly sampling with replacement, and we decided to kind of average with the understanding that averaging reduces variance. One might ask the question, are these the best things to do, or are there other ways to do something else, right? So, instead of doing uniform sampling, can we do some other more principled way of sampling with replacement, and instead of averaging, can we do something more principled to kind of aggregate these classifiers? So, the answer to both of these questions turns out to be yes, and the algorithm which does exactly these two steps, but then it does these two steps in a slightly different way by thinking about what is in some sense the best possible way to do each of these steps, will lead us to a very, very powerful algorithm called the boosting algorithm, right. So, this will lead us to the boosting algorithm, which is what we will start looking at next.